Okay, so I'll just walk through code. Where we make models. Yes, models, cool, pog. Okay, so I was given this code. Yes. So let's list all the things that this code does. It first loads in the roamer delay difference between two ephemeris models. Don't worry, I'll explain. So the roamer delay, very loosely, you can think of a center of mass or our sun, yeah, whatever. Uh, and the Earth, this distance is shorter than this distance, right? On an ellipse, we don't have a perfect circle, so as time progresses, the difference between where we are and the center of mass changes. So the roamer delay is this difference in light travel time between these two lengths. So you know light, it travels at a constant speed, c, 3 times 10 to the 8 meters a second. So if we want to solve for the time it takes light to reach where we are, we have, let's say, length 1, length 2. We expect that the speed of light times some time 1 will equal length 1, and c times t2 will equal length 2. So we can just solve for this for t. Okay. So to recover time 1, I guess I should explain what this notation is. I decided not to write down T1 and T2's equations separately because I can substitute in I for that, where I can vary 1, 2, 3, 4, 5, however much I want. So T1 equals length 1 divided by speed of light, which makes sense, right? Because we get a length divided by a length time gives us a time. Okay. So then, oh, yes, ephemeris models. Our solar system, it evolves with time. And if you put like 7 more layers and draw all the moons and the planets and all that, we would have a big system. This system we could model via ephemeris models released by NASA. These models, they calculate the center of mass of our solar system. So as time goes on, our center of mass is going to change, because like above, Um, uh, Ellipses are not perfect circles, and the radii are different between various planets. So our solar system just gets jumbled as time goes on, and the center of mass changes. It moves around, you know, goes wherever it frickin' wants. Um, and then we calculate the Romer delay between these times, the center of mass lengths. So, if we think about this just a little bit, I am streaming this because uh, the one thing I want to get out of stream, no, I want an educational stream, and I want people to come in, ask questions, have a nice time. Um, I plan for my mornings, which will be like 8 to 10 a.m. I want to stream my research every day. Just one, to get me motivated, and two, it will let me practice talking about it and all that. I personally think it's pretty cool stuff. I think people want to hear about gravitational waves. Um, yeah, other things I want to do are like book breakdowns, video breakdowns. Oh yeah, thank you, baby. That is what I like to see. Yeah, I want to watch cool videos that people usually can't access because they don't have the math knowledge and they're like turned away from it. So I would like to just watch them, pull up OneNote, describe the maths involved. I know my uncle wants to learn calculus, but he's an uncle and I don't think he wants to go back to school. So one thing I want to do is go through a calculus book. He is at an algebra level. So what I would do is start at algebra, work through the basics, then go through trig, work through those basics, upload all those videos, then go through calculus, upload all those videos. I just think Twitch is slowly not leaning, but opening up to more educational streams. Um, I know YouTube has a big uh physics science section, so what's to say Twitch won't eventually evolve into that too? Yeah, so yeah, one of my favorite streamers right now is Daniel Naroditsky. He streams chess. He's a grandmaster. Yeah, I know that man. Well, I've watched a video that him talking to an incel, and then the incel started crying at the end after like 2 hours of breakdown. Yeah, Daniel's great. Danya, he he's actually just providing in-depth grandmaster lessons to tens of thousands of people for free. It's something 10 years ago I don't think would have existed. I mean, we have the like chess YouTubers, but honestly, they're all dog. Yeah, well, that's cringe. I don't know if that's him. You might be thinking of. If you're thinking of a streamer, are you talking about Hikaru? Because all Hikaru does is play really fast chess, and he's TSM sponsored. Um, and he's like more of an entertainer chess streamer. And of course, he does the PogChamp like tutorings and all that. Yeah, I like Danya a bit more. He breaks things down a ton. Okay, I'm gonna get back to talking about this. So, we expect that eventually our model is going to repeat. The solar system will eventually end up in the exact same spot as it was, I don't know, 10 years ago, 100 years ago. I don't know the time, really. So the next part of our code, it takes this R matrix, and there's one paper that talks about an R matrix, and I don't really get it, but it basically subtracts out a function out of your results. So if you get something that's looking like this, oh god, we could subtract out the function like y equals x plus 5 or something, and it would transform our graph into looking like something this. And then we could also subtract out periodic functions like sine x and cosine x. And then we would hopefully just get something as small and as constant as possible. Uh, on the left here, you can see I subtract out, we got ones. We got a matrix of ones for some reason. And we got t's. And then we got t squareds. And yeah, I'll eventually add it to like sine x. And then cosine x. And then we'll get some nice data. Yeah. So we then get into the cool stuff, right? So I guess I'll talk about my problem here. There's this Australian group who has a conspiracy, right? Their conspiracy is that one of our older solar system models, our ephemeris models, is more correct than one of our most recent ones. And they say this because there's this weird difference in Romer delay between these two models. And they don't really know what's going on, right? It's a conspiracy. Um so my advisor, he's like, "No, it's not, you fucking Aussies. It is not a conspiracy. There's this thing called a black hole, and when it spins, it produces a gravitational wave." So let me get some pictures going. Oh god. So we got the spinning mass, right? It's going blah blah. It sucks in all the light. Haha. Light your mind, says the black hole. Um and it spins and it produces these distortions in space-time. And please, I don't think I can tell you what that really means right now, but you can think of these distortions with a little model. You know what? I actually have the picture right here. So if you have a ring of particles, right, a ring of particles, when a gravitational wave comes through, it'll distort in some directions more than others. So you can see on the left we would get an ellipse in one direction, in the other direction, horizontal, vertical, and in our research we're not really talking about the bottom one at all, where it's like diagonal distortion of rings. Yeah, so gravitational waves, they come out and they're like, oh, we're gonna just frick shit up, right? They're gonna fuck it up. They're gonna make the distances between various parts on this ring of particles different, right? From the center. It looks a whole lot like Romer delay, like I was talking about above. So, my professor says that these gravitational waves from rotating supermassive black holes are distorting space-time enough such that it looks like the Romer delay we see between the ephemeris models. So it's not a conspiracy, it's just a fundamental aspect of nature that was not taken into account before. So, what the code does next, stop. It basically grabs this other code and it takes a pulsar. Another thing to talk about. So we got a neutron star and it begins to enter its supernova process and it gets smaller and smaller, starts rotating, and there's some stuff going on in the middle that we don't really know too much about. But when the neutron star starts to rotate fast enough, get dense enough, enough energy is formed to fucking blast out these beams of electromagnetic radiation, right? So you could imagine a lighthouse. Oh, it's beautiful. That is shining a beam and rotating, right? It's going around. It's going around. It's periodic, right? It has some period. It's probably not going to change because it's perfect, right? We're perfect here. Or if it does change, it's so tiny, it doesn't really matter. So we're basically using these pulsars as a clock, a timing array, some might say, a pulsar timing array. Look it up if you want to learn about cool clocks. So what this injection code does is it grabs 100 pulsars, it injects a gravitational wave, And then it calculates the difference in light travel time between the pulsar and Earth. And we're seeing, or want to see, how often this pulsar light travel time looks like the Romer delay, which is the light travel time between the center mass of our solar system and the Earth. So, if we run this code like 117 times or something like I did, then we'll get a lot of pulsars, right? A lot of different pulsars with a lot of different gravitational wave backgrounds. And um it spits out the difference in light travel time. Hi, uh Saint Jesh Germany. How are you doing? I'm just talking about my undergrad astrophysics research right now. If if you need any math or physics help, I also offer that. I really like the idea of having a nice little community where people can just drop in and learn and get stuck with homework. Have you heard of mathematicism? Yes, I know words. I think I've heard of this, yeah. It it feels like the ideal atheism that I've always believed to be. That, like, the universe has to abide by these, like, laws of nature, laws of physics, of course, because. So I think mathematism is pretty good. What do you think? Alright, let me try and pull up some plots that I should be able to do. Um yeah, I don't know what I'm plotting actually. I will find it. I have a document somewhere that's my research. It would be great if I could find it. Aha, I don't have the code to run. Yes. Okay. Um, so yeah, if I was cool enough, I could spit out two plots that would look something like this, but a lot more dense and gross looking. And if I plotted one pulsar, it might line up with how the Romer delay looks, and then the second pulsar might not. So it basically the the Romer delay of our solar system looks like this, right? It's periodic. It gets bigger and smaller as time grows. Um, and then we map the pulsar uh, difference in times, and it could look like this. I've seen one look like this, but then around 35% of the time, we'll see it like lines up pretty good, pretty pretty convenient. Honestly, that these pulsars are sorry, that these gravitational waves are affecting these pulsar times often enough that it looks like this difference in Romer delay between ephemeris models. So, one might suspect with this that the gravitational waves are the ones causing this difference in Romer delay, and not some weird conspiracy where the older model is better. You asked me about my take. Oh, hmm. Yeah, I could see that. Um, Physicists are in this really weird state right now, and I don't really know where they're going, but, okay. So Newton had a theory of gravity, right? It was pretty pog when it first came out. It was a pog theory. And then uh Einstein came around and was like, "Okay, your pog theory, it's not so pog when we get very massive things very far away." Just wait. Um yeah, Einstein was like, "No, gravity's a field, big masses create this distortion in space-time, blah blah blah." But then black holes come around, and quantum mechanics don't really agree with what happens when you get to the center of a black hole. So physicists currently have this weird theory about like this n-dimensional space where gravity doesn't exist, and I don't know, it's quantum mechanical. It's like a black hole in a box or something, and they can't describe it mathematically yet. It's weird. um, but if eventually they might have a sound enough theory that wouldn't couldn't be described mathematically, but maybe experimentally or something. What would be physics without math? Yes, hard, hard. For some AI-like being, uh, I don't think humans could ever understand, physics without the mathematics. Alright. With the, Romer delay between ephemeris models and the gravitational wave distortion, we run these root mean squares that basically they square all the numbers in the set, add them up, square root, I think. And it's a little bit more accurate than a mean or something. I'm not too sure on statistics and all that. Oh, and then we spit all that data into a file. The next thing we do in this code is open those files, grab the columns. We grab the first column because here, I'll just pull up the code. Yeah, we have all these things around 100 to 300 nanoseconds. And there's only one column, so we have to grab the first column. It states that imaginary numbers exist in reality, and so do complex numbers. Well, yeah, if imaginary numbers exist, then complex numbers by definition would exist. Complex numbers, they feel fake, but they are some of the most, sorry. They're beautiful. They solve so many things. They allow you to grab so much data on our universe. But I don't know. All I've seen so far, like in my optics class where we discuss lenses and electromagnetic waves, that we only care about the real part because only the real part exists in nature. Because all our measurements agree with that. Yeah, imaginary numbers, they're wild. They're cute though, you know, like if A plus BI walked up, smacked my bitch at the club, I don't know what I'd do, you know? Like you're gonna resist BI? Alright. The next thing I do in this code is I run a histogram of the left one is the difference in Romer delay between ephemeris models. The right one is the difference in light travel time due to the gravitational wave. With a little shenanigans, you can see I put a line right here. What this line says is, hold on, wait, which way? Which way does this go? Ah, yeah, so the gravitational waves, we put an upper limit on how big their distortion can be. So we put it at like here, the 0.3 mark, the mean of all of this. I think I printed out, yeah, x line mean y, where y is this. So it takes the mean of the right and it slaps that mean right down into our Romer delay between ephemeris models. I will get to that one sec. I'm so close to being done with this explanation. Oh jeez. Yeah, so everything below this mean on the Romer delay section, everything below the mean around 0.3, we suspect. No, this is how often these two things look similar enough to call it good. the mean is where we have to stop and say, nah, this isn't good, and we put that mean. It's around 0.3. So we slap it here and count how many times the Romer delay looks like the gravitational wave effect. So really quick, I'm just going to print the mean y. Yeah, so we can see the mean is around 277 nanoseconds. What is this one? Oh yes, this prints how many times, how many data points lie under this line, and we get around 6,042. And then if we divide this hist count by the total count, we get around 36%, 35.65%, which it's good enough. I think there's like an update to, an update to the question that we're going to discuss next week, but it's looking good. I think we have a solution to our problem. I'm also going to take this graph and make it look sexy because that's my assignment for today. So let me read this. My take on two fermions can never have the same set of quantum numbers to describe them. They are forced to be individuals. They must be distinguishable via their quantum numbers. They will never be found together. It's as if there's a repelling force keeping them apart. This is the mathematical origin of the Pauli exclusion principle. All that was required to achieve the Big Bang was an exclusion principle that converted bosons into fermions. I will say, as a undergrad who's never taken a particle physics course, I find it really hard to remember all the stuff about particle physics. So I don't really know, and I haven't learned directly about the Big Bang. Like we talked about moments after it in astrophysics, and we didn't really talk about it at all. In cosmology, we just talked about the expansion. So, I don't know what happened for the Big Bang to happen. The Pauli exclusion principle. You, you, you want to know what's cool? Linus, hold on. This is Linus Pauling, right? Or am I dumb? No, it's Pauli? Of course. Okay, maybe I was thinking of something else. Let's learn. Yeah, currently science doesn't know what happened for the Big Bang. Right? We know immediately after. We know like nanoseconds after what happened the Big Bang and how fast all these fusions happened and effects. What I do know is we're trying to figure it out, and one way we try to map out what happened for the Big Bang. I think Berkeley is doing this. They are taking our universe and tracing the gravitational waves back in time. Because these gravitational waves apparently leave a residue on our spacetime. So we can follow them back. Or something like that. Sounds cool. Time is treated as something of a wholly different nature from space. True. Where space is static, time is dynamic. When time is properly understood as imaginary space, which is orthogonal to real space, its true role becomes crystal clear. Just as real space is not understood to move, nor should imaginary space be understood to move. Movement is something entirely different from space and imaginary space-time. Movement is energy. Energy moves through both real space and imaginary space. Now this holds true. This is the theory of relativity. Time and space are not the same. They are orthogonal to each other. We have a four-dimensional space-time, for to have a basis, you have to have an n-dimensional basis. You have to have four orthogonal in n-dimensional bases, you need n orthogonal vectors or directions. So to have a four-dimensional space-time, there's this weird disagreement between space and time. I can show you some cool stuff. I guess I don't need to draw it. Alright. So, space-time is pretty cool. We all know the Pythagorean theorem, right? A squared plus b squared equals c squared. This holds in Euclidean space, Euclidean geometry. But when you introduce time, you can't just add a t squared. Look, we've tried to do it adding t squared, but under the Lorentz transformation, a transformation that takes equations from one coordinate system to another, it's a transformation. We know that the laws of physics should hold from one coordinate system to another, and the Lorentz transformation is not invariant when there's a plus sign. When there's a minus sign, though, it is invariant, and special relativity goes nuts. We get all this hyperbolic geometry. It's pretty cute. I like it. It's cool. Space, though, is not static. If I'm thinking about it right, because we have these massive objects. Oh wait, sorry. Space is static, but space-time is not. Space-time bends and curves and creates these massive wells of gravity. Space just exists, and time always goes forward. Just a question, Saint. Where do you hear about the stream? 'Cause this is my first stream and you already popped in. What was I doing? Who am I? I was talking about space. Time? Space time? Time could be treated as imaginary space. There are three space dimensions, hence three time dimensions. Means we live in a six-dimensional space-time. Also, this space-time can be absolute. It doesn't have to be relativistic. We always travel with the same speed in space-time. Just the space-time ratio differs. Hmm. I've never heard about anything about this theory. I don't think I'm on the right page. Yeah, I'm on six-dimensional space, not space-time. Oh, complex space-time. Here we go. The notion is entirely mathematical. A tool. Yeah, well, come on, Wiki. In 100 years, it might be applied. But I guess right now it still just remains as a tool. The metric tensor being imaginary. The metric tensor, it measures the length between 2 points on a coordinate system. It feels too loose to base anything off of. It feels like with Euler's formula, time dilation, length contraction, and mass increase are all absolute effects, not relative. Let's look up the quote. What book are you referencing? Ah, yes, the God equation. Are all absolute effects, not relative. Euler's formula allows the absolute ether theory of Lorentz and Poincare to be fully resurrected and to become infinitely more powerful than Einstein's ridiculous relativity. Hmm. Is this book anti-Einstein? I just want to get some discussion on this. The ions. Is this just a book on field theory? Oh yeah, that's a good idea. Oh, it's by that guy, Mr. Kaku, Dr. Kaku. Or is it this one? The God Series, Book 6 of 32? Huh? Okay. Are there really 32 of them? Oh, I see. Euler's formula is beautiful. I love proving it. You can just do it with series and sequences. I don't want to read the God Factory. Why are they talking about the Illuminati? There's equations in this book? The Illuminati? What's going on? The Riemann sphere? The soul? Oh. I mean, it looks cool. This book, I don't know. Why do they hate Einstein so much? Is the assumption of the book just like, this isn't a bad thing if it is, by the way, it's just, if Einstein is wrong, or if there's just a better theory? Is this just a better theory? Do they hate Einstein? What does the Illuminati have to do with this? Oh, God. I'm interested. I might pick up the book. Pythagorean Illuminati. What is going on? This guy wrote a Brad Gum? This man likes this book. Is that you? He's really seeking for enlightenment. Goals. Okay, whatever you say, Brad Gum. What? I'm so confused right now. You know this? I feel like I've walked into... I don't know. Am I getting radicalized? They have 63 books? Ah. This is just on Pythagoras. You want me to put this on my read list? We're really going down the rabbit hole. You may think you are familiar with three of the most important biblical figures: Abraham, Moses, St. Paul. Think again. Ever heard of a guy called Pythagoras? Euler? Hmm? The 12 mathematicians? Hmm? Didn't think so. A scientific version of Gnosticism? A scientifical version of the doctrine taught that the world was created and ruled by a lesser divinity, the demiurge, and that Christ was an emissary of the remote supreme divine being, esoteric knowledge, gnosis, of whom enabled the redemption of the human spirit. How is Pythagorean Illuminati connected to gnosis? They believe, the Gnostists believed that the death and suffering of Jesus were things that only appeared to happen, or if they happened, didn't really happen to the core of Jesus' spiritual reality. Okay, so analogy time. Gnosis is Pythagoras. Jesus' suffering is mathematical equations. Everything is mathematical. You know, even these mathematic religions I can't get behind. I just don't think they're for me. Alright, class time. Time to get doxxed. Oh wait, no, I have to make an image. Hmm. They attack Christianity, Judaism, and Islam as well as Buddhism, etc. 1. Abrahamism, no mathematics. 2. Eastern religion, some disguised mathematics. 3. Science, incomplete mathematics. 4. Illuminism, complete mathematics. Alright, I guess what I should really look up is Illuminism. Oh no, wrong one. Too much this though? I don't like this guy that much, but I know he's smart. I lack coffee. Attack on Buddhism. It's embarrassing to place Buddhism on a par with Illuminism, to put meditation on par with ontological mathematics. How can anyone take Buddhism seriously when it rejects Euler's formula, Fourier analysis, Riemann geometry, Riemann spheres, Leibnizian monadic calculus, the mathematics of zero infinity singularities, and so on? That sounds great, but the mathematics of singularities is where general relativity and uh, spe- uh general relativity and quantum mechanics, that's when it's over. Okay. So, if we can apply this illuminism to quantum mechanics, we might be getting somewhere. I think so. Look, you know what that pyramid just told me? It's a proof, really, that every sequence of numbers is Illuminati. Illuminati? Hmm? Hmm? Triangle? I think not. I think not. Only 0 less than x less than infinity corresponds to reality, and x equals 0 and x equals infinity are non-ontological. Just one sec. Hello, I can spell. I see. They do not exist. Illuminism, though, 0 less than equal to x less than equal to infinity, i.e. materialism and idealism are both true and dissolubly bound mathematically. How does tacking on an equal sign to the equality mean that something like materialism and idealism are true? That is pretty. Whoa. Is this even about illumination? No, it's not. I'm sorry I led you down this. And that one viewer we lost. Well, if no one's gonna do it, then I guess I'll be the first video to talk about illuminism. Hey YouTube, what's up? Math theory coming at you. We're gonna tack on some equal signs. Call it good. I'm not. I'm. I'm not dissing on what you're bringing to the chat, by the way. I'm just genuinely confused about all of this. I close my MATLAB. I want this X line to be thick. Yes, I would like more. I will take a label, yes. Well, I'm glad that worked. That's pretty good. I'm probably gonna upload these videos to my YouTube too. I want to get a big library about just mathematics and physics and just discussions. I think it would be nice. What mean is God? Mean time difference. Created by gravitational wave at a see how it looks. Uh-oh. Uh-oh, spaghetti. Uh-oh. Uh-oh. Do you mean? Okay. I leave for now? Hey, well, thanks for stopping by. If you liked it, follow for next time. I'm gonna try and stream a lot more often. I hope you have a nice day. See you next time. Thanks for the follow. I'm so confused. What's wrong with this? Maybe they don't like the words. Can I just go like mean? Is that enough? No. Why is this happening to me? What do you mean? Maybe not that. Really no line thickness? Can I add 2 lines? I take 10 lines. I squeeze them together. I make it look like 1 line and tell no one about this. If you tell my advisor, it's over. I can make line color. Maybe I'll do that. What would pop? I think black pops. Maybe a red. Wait, line width.